This is a video to help you with the data analysis for the free-falling objects experiment. In Table 1, we're going to enter the time values that we got from the data collection experiment. I'm going to enter in the values that I got from my experiments. Having entered our data, we can start with a data analysis. In question 2, we are asked to calculate the range for each height. To do this, look at the time measurements for each height. Notice which one is the largest. In this case, the largest value is 0.270. And notice which one is the smallest. The smallest is 0.255. Subtract the largest from the smallest. To do this on a calculator, we can type in 0.270 and subtract that from 0.255. Pressing enter gives us the value. The value is 0.015. That is the range. Continue calculating the range for each of the remaining measurements for each height. Having calculated the range, it is now time to look at question 3. In question 3, we calculate the averages of the drop times at each height. To do that, we're going to add the readings together and divide by 3. For example, for the first set of measurements, we will do this. First, we're going to clear our calculator and then add 0.255 to 0.270 and add to that 0.266. Notice that I didn't have to type in the leading zero in each of these values. I'm going to press enter. This gives me my sum of the 3 values. I will now divide that total by 3. When I press enter, I get my result. I want to round this result to 3 decimal places. So the answer is 0.264. I'm going to type that in here. And then I'm going to continue to calculate the rest in the same way. For part 4, we need to calculate the square of the average time values that we have calculated. To do that, we can use a calculator, and let me show you one example. For example, if we want to calculate the square of 0.264, we type 0.264. Once again, the leading 0 is optional. And then we find the square button on our calculator, press square, and on this particular calculator I have to press enter to see the result. And there's my result, 0.0696. Rounded to 3 significant digits, the answer is 0.0697. So I'll go back to my data sheet and I'll type that number in, 0.0697. 0.697. I will use the same technique to calculate the rest of the squares. In part 5, we need to plot a graph of the drop height versus the drop time in seconds on a sheet of graph paper. I'm going to show you how to do that. I've got my graph paper here, and first, before I start plotting my graph, I want to look at the range of the data that's to be plotted. So let me go back to the table here, and let's look at the range now, not of the values for a particular height, but the values that need to be plotted on each axis. We'll be plotting the height, the drop height, on the y-axis. So the y-axis must go from 0 to 1.8. And I'll be plotting on the x-axis the average time taken, and that must go from 0 to 0.622. Going back to this graph paper, we can start by sketching the axes. Ideally, you would use a ruler to draw these lines. And label them. That's height in meters. That's time in seconds. So the next step now is to choose an appropriate scale. Notice how I have drawn my axes to make maximum use of my graph paper. We don't want to waste space on the graph paper in the sense that our data points should be distributed over the area available. This will allow the graph to be read as clearly as possible. So look, now what's left is to choose appropriate scales for the y and the x-axis. Let's start with the y. First, let's count how many squares we have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. So I have 23 squares on my y-axis, and that needs to cover a range from 0 to 1.8. Now we don't want to divide 1.8 by 23 because we will end up with a very inconvenient scale to use. We can put our 0 in place there. What seems like the easiest thing to do is to make our scale go from 0 to 2 and to use 20 squares on the vertical axes, in which case we will see that each square corresponds to 0.1. Now we don't want to label every single square because that would lead to quite a messy axis. So instead we'll choose an appropriate what we call a major mark. So looks like labeling it every 0.5 meters would be reasonable. So let me do that. 1, 2, 3, 4, 5. So this would be 0.5 of a meter. 1, 2, 3, 4, 5. This would be 1 meter. 1, 2, 3, 4, 5. this would correspond to 1.5 meters, and then finally 1, 2, 3, 4, 5, that would correspond to 2 meters. The next step now is to choose a scale for the time axis. So once again, we'll count the number of squares that we have, or the markings that we have on this axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44. So on the x-axis, I have 44 squares, and the data range that we want to represent on that axis goes from 0 to roughly, well, it's actually 2.622 seconds. So once again, it seems that the most convenient scale to use would probably to use 40 squares and go from 0 to 0.8. In such case, we can see that if we divide 0.8 by 40, we get, so doing this on my calculator, 0.8 divided by 40 is equal to 0.02 of a second. So that would mean each one of these minor marks here would correspond to 0.02. So therefore, each fifth mark, 1, 2, 3, 4, 5, would correspond to 0.1. So I'm going to label these for every 5 of these squares, and that should give me an axis that is not too cluttered. So let me finish doing that. 1, 2, 3, 4, 5. That is 0.2. 1, 2, 3, 4, 5. This is 0.3. 1, 2, 3, 4, 5. 0.4. 1, 2, 3, 4, 5. 0.5. 1, 2, 3, 4, 5. 0.6. 1, 2, 3, 4, 5, and 0.7. I need not go any more because I know I don't have any more data points beyond, there are no x values that are beyond 0.7. So I will stop there. Let me clean off these temporary calculations. And now we are ready to start plotting our points. Let's look at our data table. The first point that we want to plot is, the first data point is 0, 0. That's easy to do. Zero, 0. I didn't mark my 0 over here, so let me do that. That's our first data point. Our first data point is at the origin. Our second data point is at 0.3 meters, and the time is 0.264. Let's go over here. 0.3 meters corresponds to 0.1, 0.2, 0.3. So it's got to be along this line here, and it corresponds to 0.26. So this is 0.22, 0.24, 0.26. Now the actual result is 0.64, but we cannot really manually plot it to that fineness. It doesn't really matter anyway, because there is some spread in the data that is greater than that 0.004 seconds. So that's our second data point right there. Let me put that in red. There we go. Our third data point is 0.6 and 0.36. Again, I'm forgetting about the 1 at the end for the purposes of plotting the graph. So 0.6 and 0.36. This is 0.6 and 0.36. There's 0.3, 0.32, 0.34, 0.36. Is right there. So when we're plotting the graph, we get to appreciate that we have chosen axes that are easy to work with. So it's very easy to identify, for instance, 0.6 on here, and easy to identify 0.36 on this scale. Let's continue. 0.9, and here I'm going to round this to 2 significant digits to result in 0.44. 0.44 would be quite easy to plot using our setup. So 0.9 and 0.44. This is 0.9. There's 0.4, and this is 0.44. Next point is 1.2 and 0.52. 1.2 is here, and 0.52, there's 0.5, and that's 0.52. I'll switch to circles because they're easy to draw from me. Oh, okay, I'll fill that in. It's just my pen ends up deleting things if I go over it too many times. Let's plot the next point, which is 1.5 and 0.58. 1.5 here, there's 0.5, 0.52, oh sorry, there's 0.5, 0.52, 0.54, 0.5, oops, sorry, 0.58 should be up here. There we go. And our last data point, 1.8, 0.62. .8 is over here. This is 0.6 and this is 0.62. So there's our graph. Having drawn our scatter plot of the data points, we can sketch a line that goes through the data points. So in this case, just trying it freehand, getting a curve like this. Let's see if we have all the elements of a good graph. Our axes are labeled with the unit, so we're explaining what the quantity is and the unit of the quantity, which is meters, and we've done that on the x-axis as well, time, seconds. And now we just need a title on the graph, so we can label this drop height versus drop time. And there's the finished graph. For part 6, we want to plot drop height versus the drop time squared. So we'd like to plot this quantity on the y-axis and the average squared on the x-axis. So we're going to use the same technique that we used before. First, start out by sketching our axes, or drawing our axes. Now, we know from our previous experience that using a scale where each square represents 0.1 of a meter seems to work quite well for the y-axis. So we can use that scale again. One, two, three, four, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. We've got the y-axis, and of course this is 0. Now for the x-axis, we know before that there are roughly 40 squares on the x-axis. And the range of values that we need to plot are from 0 to 0.387, which is roughly 0.4. So 40 squares on the x-axis, we have 40 squares, and we need to plot a range of 0 to 0.4. So we can see, I've rounded that up, and we can come up with a nice convenient scale here, because 0.4 goes into 40 very simply, which is equal to 0.01. So each square is going to represent 0.01. So now we can start labeling it. So every 5, 1, 2, 3, 4, 5 is equal to 0.05. 1, 2, 3, 4, 5, 0.1. 1, 2, 3, 4, 5, 0.15, 1, 2, 3, 4, 5, 0.2, 1, 2, 3, 4, 5, 0.25, 1, 2, 3, 4, 5, 0.3, 1, 2, 3, 4, 5, 0.35, 1, 2, 3, 4, 5, 0.4. Now we have to label the axis, and this will be time squared in units of a second squared. Let me just put an arrow there to indicate the direction of the increasing numbers. I'll just remove my temporary calculations, and we are now ready to start plotting our data points. Our first data point is 0, 0. Our second data point is 0.3 and 0.07. So 0.07 will be around here, and then the 0.3 is right there. Now let's do the next one. That will be 0.6 and 0.13. Here's 0.6, here's 0.1, and 0.13 is 1, 2, 3. Next point is 0.9 and 0.192. There's 0.9, 0.192, so there's 0.2, there's 0.19. Do my best at making a 2. There we go. Actually, let me make that just a bit smaller so that the marker is the same as the others. There we go. Next data point is 1.2, 0.27. So I've rounded that to two significant digits to make it easier for me to plot. I will try and make it 0.266 by making it in between 0.26 and 0.27. So this is 1.2 meters, and it's 0.266. So this is best I can do there. And 1.5 is 0.336. 1.5 is 0.3, 1, 2, 3, and put that there. That's 0.36, or 0.336, sorry, that's 0.336. And our last data point is 1.8 on the y-axis and 0.387 on the x. 1.8 is here, and I've forgotten that number. It's 0.387. There's 0.35, 0.36, 0.37, 0.38, so 0.387 is about there. Now this is, we plotted our data points on the scatter plot, and the next step now is to sketch a line through these, and this looks quite linear, so I'm going to have a go at sketching a straight line. That looks pretty good with my data, and what's left now is to check that we have all elements of the graph. We have our axes labeled with the unit, the correct unit, and we simply just need to give it a simple title, and this is drop height versus, this is abbreviation for versus, drop time squared. And that's the end of our graphing. We now have our data calculated and graphed, and we can now look at it and start to draw conclusions from it.